Welcome to Chapter 10, the Part 5 screencast for liquids, solids, intermolecular forces, and phase changes. Picking up from the last screencast, the heat or enthalpy of fusion, which we symbolized by delta H sub FUS for fusion, is the amount of energy that's needed to convert a solid into a liquid, i.e. it's melting. The heat or enthalpy of vaporization, which is symbolized by delta H VAP for vaporization, is the amount of energy that's needed to convert a liquid into a gas, i.e. it's boiling. And both of these, as we've discussed before, are measures of how strong the intermolecular forces are within a given substance. Things that have a high enthalpy of vaporization or high enthalpy of fusion are going to have high or strong intermolecular forces that need to be overcome or partially overcome. Substances with small or low enthalpies of fusion and or vaporization have weaker intermolecular forces. Here are the values of delta H of fusion and delta H of vaporization of some common substances like ammonia and benzene and water. And you can see that they vary. Some are smaller, some are larger. And again, remember that they are relative measures of strength of intermolecular force. So you should be able to answer questions. Certainly, even without the numbers, you could make some guesses. But with the numbers, you could say, well, of these, which substance has the weakest intermolecular forces? So I'll give you a moment to think about that and see what you come up with for an answer. And hopefully what you say is helium has the smallest delta H of fusion, the smallest delta H of vaporization, by quite a lot, in fact, and it's going to have the weakest intermolecular forces, and that makes sense because helium does not have a dipole, it doesn't have hydrogen bonding, and it's a very small molecule, so it has very weak London dispersion forces. All these other substances are larger, have dipoles, or hydrogen bonding, so you'd expect all of those to have much, much higher or stronger intermolecular forces. Now, if instead the question is which substance has the strongest intermolecular forces, then again, we can look at the formulas of the compounds. We can predict intermolecular forces based upon type of intermolecular force due to the structure of the molecules. And if we have delta H of fusion and vaporization values, we can, of course, use those as measures of strength of intermolecular force. So think about it a moment, make your prediction of answer. And note, if we use delta H of fusion values, then benzene has the largest delta H of fusion of these compounds, and so we would say that benzene has the strongest intermolecular forces. But if we use delta H of vaporization values, note that the largest value is the 56.9 kilojoules per mole for mercury, but that's not really an intermolecular force technically. This is still a delta H of vaporization, but mercury is a metallic compound, it's not molecules, so technically that's not going to be an intermolecular force. So the next highest is water, which has almost as high delta H of vaporization, 40.7 kilojoules per mole. And note that the delta H of fusion of water is the second highest behind benzene. So this is just meant to indicate that depending upon what exact quantity you're looking at, you may get differences in which substance appears to have the strongest intermolecular forces. And note that the overcoming the intermolecular forces to take a solid and turn it into a liquid are somewhat different than the intermolecular forces you overcome taking a liquid and turning it into a gas. Here, you're just changing substances that are locked in place in a solid into where they can move around relative to each other. But they're not totally separated, whereas with delta H of vaporization, you're actually completely separating the molecules from each other as you go from liquid phase to gas phase. Okay, now let's go back to something we did a little bit, hopefully, in thermochemistry, which is heating substances. And perhaps you remember a little bit about heating curves and also how to do these sorts of calculations. So just as a reminder, if we have no phase change, then the heat involved is the product of the mass of the substance times its specific heat times the temperature change it undergoes. But if we do have a phase change, then the heat involved in the phase change is going to be the amount of the substance, which we usually do in moles, times the delta H of whatever phase change. So delta H of fusion for melting, or delta H of vaporization for liquid going to gas. So here is a heating curve. This is for water. And notice what we're doing is we're graphing heat added on the x-axis versus the temperature on the y-axis. And if we start with water as a solid, i.e. ice, at negative 25 degrees Celsius, we have to add some heat to make it, first of all, increase its temperature gradually to 0 degrees. And then once it hits 0 degrees, ice will now start melting, and it will turn into a liquid, and the temperature remains constant. So we have a constant temperature at 0 degrees, even though more heat's being added. Eventually, all of the ice has turned into liquid, and now as we keep adding heat, the temperature of the water increases. Eventually, we hit 100 degrees Celsius, at which water starts boiling. Temperature stays constant while the water boils, even though more heat is added. And then eventually all of the water liquid has turned into steam or water vapor, and now we keep adding heat and the temperature of the vapor goes up. Notice from the quantities of heat added, it doesn't take too much energy to increase the temperature of ice. It takes quite a bit of energy to melt the ice. The slope here is reasonably steep, so it takes a reasonable amount of reasonable amount of heat to increase the temperature of water compared to other substances, but it's nowhere near the amount of energy needed to change the phase from liquid to gas. So notice how much heat's added here. And then again, once you've changed it into a gas, it doesn't take too much heat to change the temperature, relatively speaking. So let's just do one practice example of these sorts of calculations. So example 14 is a heating curve for sodium. We'll start at room temperature. We have some data from the previous example, and the molar heat capacity of sodium, which is assumed to be the same for all phases, is also given here. And previous information are the melting and boiling points of sodium, as well as its delta H of fusion and delta H of vaporization. So here's all the information kind of compressed up at the top, and now we'll make a heating curve, and notice that we will start at room temperature, 25 degrees Celsius, and since sodium's melting point is almost 100 degrees Celsius, it starts as a solid. If we add heat, the temperature will rise until we hit 97.8 degrees Celsius, and the substance is a solid during this whole time, so the amount of heat added will be Q equals, and now here instead of mc delta T, we'll use nc delta T. And the only reason we're doing this is because the specific heat was given in joules per Kelvin mole rather than joules per Kelvin gram. So we're going to just say, let's assume we have 1 mole of sodium times 28.2 joules per Kelvin mole times a temperature change of 72.8 degrees Celsius, or 72.8 Kelvin, as it goes from 25 degrees to 97.8 degrees Celsius, and that works out to be a little over 2,000 joules. Okay, now we're at 97.8 degrees Celsius. The solid starts to turn into a liquid. We continue adding heat while the solid melts, and the enthalpy change for that process is going to be given by Q equals N times delta H, and both of these are for fusion. Remember, we're dealing with 1 mole, and the enthalpy change for fusion for sodium is 2.64 kilojoules per mole, which is 2,640 joules per mole, and so 2,640 joules for the phase change. just keeping everything in the same units. Now, once all of the sodium has melted, as we keep adding heat, the temperature of the liquid sodium will increase, and it'll keep increasing until we hit 883 degrees Celsius. So notice our graph is not exactly to scale here. And the Q for that is the same idea as the Q for the solid, but a much bigger temperature change. And in many substances, the specific heat will be different for the liquid phase than for the solid, but here we're given that it's the same for both. So that works out to be 22,000 and something joules. And then if we keep on going, once we hit 883 degrees Celsius, then the liquid will boil, and the heat of vaporization will be the number of moles times the delta H of vaporization, which is 1 mole times 89.6 kilojoules per mole, which is 89,600 joules per mole, and that works out to be 89,000 joules. And we could then keep going, add more heat, and increase the temperature of vapor, sodium vapor. But basically, here are the amounts of energy required for each step. And if we wanted the total, we could, of course, just add all that up. So that's it for this screencast.